In the previous lecture, we have modeled the CPM controller with ramp compensation. So today we are going to, based on the model we have derived, we are going to try to derive the transfer function of the CPM controller. So first, let's have a review on the CPM model we have derived. So basically, we have an expression for small signal duty cycle in CPM with ramp compensation. So duty cycle equals to Fm times controlling current small signal minus inductor current small signal minus Fv times output voltage small signal minus Fg line voltage, input voltage small signal. So this is a unified model for the CPM controller with ramp compensation. And besides, for the power conversion power converter circuit itself, we can also use similar formulas to represent the output voltage and the inductor current. So basically, we have the small signal output voltage to be equal to GVD times small signal duty cycle plus GVG small signal input. And for the inductor current, IL small signal, it is a function of the duty cycle and the line input too, right? So we denote GID as the coefficient for small signal duty cycle, and we define GIG as the coefficient for small signal input voltage. So where we have introduced the two transfer functions right here, GID is defined as the ratio between inductor current and duty cycle under the condition that the line input is 0. And GIG is defined as the ratio between inductor current and line input under the condition that duty cycle small signal is 0. So based on the three formulas, we can plot the block diagram of the entire system. So first, let's plot this one. So based on the three formulas, we can plot the block diagram of the controller and the power circuits. So first, let's plot the CPM controller block diagram. So we have here as the control input, and control input goes to an operator here. So here is the inductor current minus, right? And here is the difference between IC and IL. Then we go to another operator to minus FV terms. So here is the gain stage FV, and the input of FV is the output voltage, right? And for this block, is another minus sign here. So the gain here is Fg, and this input is Vg small signal, and output of this operator goes to and gain stage of Fm. And this, it goes to the duty cycle, right? Duty cycle. So based on the duty cycle, output voltage, and the line input, and those two formulas, we can establish the block diagram of the power stage. So basically, here is the duty cycle, right? Duty cycle have two branches. One is GVD parts, and one is GID parts. For the line input, it also has two parts, right? One is GIG, and the other one is GVG. So then we look at the output voltage, right? Output voltage equals to GVD times D plus GVG times VG. So here we go to another operator plus the output is, right, small signal V, right, GVD times D plus GVG times VG. So this goes to the FV parts. And then we look at the last formula. So IL also contains two parts. So we add another operator here. So one is GIG times VG, and the other one is GID times D. So the output is IL small signal, and this goes to the beginning. So here is the line input, right? Line input. So this input goes to here and also here. So, but the input begins from here. Okay. This is the output, right? Output. So if we look at this block diagram, right? There are two parts. So basically, this part the blue part is the CPM controller model. And this part is the power processor model, right? So looking at this, so here we have a plus sign. Plus. Looking at this block diagram, so we remember we have previously discussed the feedback theorem. So here we can apply the feedback theorem. For the feedback theorem, remember we can choose a point to break the loop and insert the small signal perturbation. So this point must be a must for the entire path. So for here, this point is the ideal place to insert the perturbation. So we break the loop here and add an operator. So here is the small signal perturbation of VZ cap. And then we add this VZ into this loop, right? So here we mark this as minus VY cap. And the output of this operator will be Vx cap. So based on this feedback theorem, we can try to first analyze the closed loop control to output transfer function. So just to apply the feedback theorem we have derived. So here I just gave you the definition, right? So basically, based on feedback theorem, the control to output transfer function is GVCS is defined to be the ratio between output voltage and controlling input under the condition that the perturbation of Vz is 0. And the line input is 0. So the result, right, we have derived here. I just put the results. Result will be equal to G infinity Vc times Ti divided by 1 plus Ti plus G0 Vc times 1 over 1 plus Ti. So Ti is the loop gain transfer function, right? And G infinity Vc is the closed loop control to output the ideal forward gain, right? And G0 Vc is the direct forward transmission gain. So next we mark this equation as equation triangle. Then we can try to derive those three parameters one by one. So first, let's look at the Ti, which is the loop gain transfer function. So basically, Ti is defined to be the ratio between Vy and Vx, right? Vx. So means that loop Vx signal goes around the loop to Vy. So equals to Vy divided by Vx. Under the condition that the controlling input is 0. And meanwhile, the line input is 0. So the only small signal perturbation comes from the inserting signal, right? Inserting signal. So basically, the feedback theorem we have derived tells us that. So we can check, right? Check this block diagram. If Vg is 0, then here is 0, right? If Ic is 0, so here will be 0, right? Here will be 0, right? So the Vy is represented by Fm times GID, right? GID goes here, right? GID goes here. Ic is 0, GID goes here, right? GID times Vx goes to here and goes to this operator. And the other part is Fv times V, right? For V, since Vg is 0, so Vg is 0, here is 0, 0. So the output voltage V will be just equal to GVD times D, right? So GVD times V times Fm, Fv goes here to this input of this operator and then goes to Vy. So basically, by the simple analyzing and simplifying the block diagram, we can see that the loop gain will be equal to Fm times the sum of two parts. One is GID, and the other one is Fv times GVD, right? GVD. So mainly because that there are two feedback parts. Okay, next, let's look at the second parameter, which is G infinity Vc. So G infinity Vc is called the closed loop control to output. Control to output ideal forward gain. So the definition for G infinity Vc is output voltage divided by the control input under the condition that the line input is 0. And Vy here is not to 0. So we have to adjust the injection signal here to now the Vy to be 0. So basically, we look at the block diagram here, right? So first, the line input is 0. And secondly, the Vy is not to 0. This means that if we look at Vy, right, Vy will be equal to Fm times the IC minus IL minus Fv times V, right? This part is gone, right, 0, because line input is 0. So Vy now to 0 means that the IL minus IC minus IL minus Fv V cap is now to 0. And secondly, let's look at the output voltage V, right? Because the Vg is 0, right? So here is 0, here is 0. So V will be relatively simple. So small signal V will only be impacted by the Vx here, right? So it equals to GVD times Vx cap. And thirdly, let's look at the IL, right? IL, because this branch is 0, so IL will only be impacted by this branch, Vx. So IL cap equals to GID times Vx. So those are the three critical formulas based on the condition that Vg is 0, Vy is not to 0. So by combining those three formulas, we can derive the ratio between output voltage and the controlling input. So here it's going to be equals to GVD divided by GID plus Fv times GVD. And if we look at here, right, we will see that the Ti and the denominator share the common part, right, common part in the bracket. So we can introduce Ti to here to simplify the expression. So this will be equal to GVD times Fm divided by Ti. So second parameter is done. And next, let's look at the G0 Vc, which is the direct forward transmission gain. So G0 Vc is defined to be the ratio between the output voltage and control input voltage IC cap under the condition that line input is 0 and Vx is now to 0. So this time, Vx is nulled by adjusting in injection signal here to make sure that Vx is 0, right? So you will see that if Vx is 0 and Vg is 0, So both are 0. So the output voltage, right, will be 0 plus 0. Here is 0, 2. So output voltage will be also naturally equal to 0. So this will be relatively simple. So just equals to 0. So therefore, we have fully derived those three parameters, right? So Ti, G infinity, Vc, and G0 Vc. Then we can insert into this function to simplify it. So basically, we can find that the GVC transfer function will be equal to Fm times GVD divided by 1 plus Ti. And this will be equal to, we insert the Ti to here, right? Ti's expression is here, to here. So we can further simplify. The numerator is Fm GVD, and denominator is 1 plus Fm GID plus Fv GVD. Okay. So now let's erase the right-hand side of the blackboard. So we'll continue to derive the following parts. Okay, we have erased the blackboard. Now let's try to derive the other transfer function, which is the line to output transfer function. So first, we write the definition for line to output transfer function accordingly. So basically, this is GVG, right? Under the condition of the current program control. So we put the CPM in the subscript. So this is defined to be the ratio between the output voltage and the line input, under the condition that the Vz injected small signal is 0, and meanwhile the controlling input small signal is 0. So this only reflects the impact of the line input to the entire system. So previously, the feedback theorem tells us that this can be also be decomposed into two parts. So which is G infinity Vg CPM times loop gain plus over 1 plus loop gain plus G0 Vg CPM times 1 over 1 plus loop gain. So again, right, this formula contains three parameters. Ti is the loop gain. So previously we have derived the Ti's transfer function. And G infinity Vg is the ideal Ford gain, right? Ideal Ford gain. So G infinity Vg is defined to be the ratio between the output voltage and the line input under the condition that the controlling input is 0 and Vy here is not to 0. So again, right, let's analyze what does this mean, right? First, we know Vy to be 0. Secondly, we have IC equals to 0. IC small signal equals to 0. So first, let's try to read this message. So Vy now to 0. And IC is 0. So here is 0. So means that this output will be only affected by IL, right? By IL. And Vy is now to 0, so that this is also now to 0. So based on this operator, we can establish a formula or equation here. So basically, here is minus IL. Right? And this branch is FV, minus FV times output. And this branch is VG times FG, right? Also negative sign here. This is now to 0, means it equals to 0. And secondly, let's look at IL expression, right? IL expression. So will be the combination of this GIG times VG and GID times Vx. Thirdly, let's look at the output voltage expression. So based on this operator, we can analyze, right? So it's equals to Vx times GVD. Plus Vg times GVG. So again, we obtained 3 formulas here. So by combining those 3 formulas, we can solve the ratio between output voltage and line input. So this can be solved as a fraction. So the numerator is Fg times GVD minus plus GIG times GVD plus minus GVG times GID. And denominator is minus bracket GID plus FV times GVD. So we compare the denominator and the expression of Ti. Again, we see that there is a common parts. So next, let's look at the third parameter here is the direct forward transmission gain. So we write the definition for G0, VG, CPM. So it is defined to be the ratio between the output voltage and the line input voltage under the conditions that the IC is 0, small signal is 0, and the Vx is not to 0. So Vx is now to 0. And IC is 0, right? IC is 0. So the output voltage will only be impacted by this one, right? GVG parts. So it equals to VG times GVG because here is 0, right? So that the ratio between output voltage and GVG will be equal to this coefficient. Okay, next we can insert the Ti, G infinity, and the G0 into the line to output transfer function here, right? So we can derive that. We can obtain the complete expression for this line to output transfer function. So which is also a long fraction. Denominator is 1 plus Fm GID plus FV GVD. And the numerator is GVG minus product of Fm, Fv, and GVD plus Fm times VG times GID minus GIG times GVD. That's the line to output transfer functions complete expression. So in this section, we have derived the transfer function of the equivalent circuit block diagram of CPM controller with ramp compensation. So in the following parts, we are going to introduce a specific buck converter example to show you how we can calculate the transfer function.